Okay, what I'm about to show you is something that will make your life of finding the derivative a whole lot easier, and you're kind of going to hate me for making you do the limit definition of the derivative, but it's okay. I'm used to it. So we're going to find out something called the power rule that's going to allow us to find the derivative of functions a lot easier, okay? And so it's all based around powers. So first of all, let's talk about the constant rule. The derivative of a constant function is 0. So this is honestly, if we think about it, it's kind of a no-brainer. Because remember, the derivative is referring to the slope of the tangent line. And we talked about the fact that if your function is a line, then the tangent line is the same as that line, okay? Or it lays against that line. So the derivative, or the slope of the tangent line, if we've got a constant function, a constant function is a horizontal line. So for example, this one right here is f of x is equal to -3, okay, or y equals -3. A constant function is a horizontal line. What's the slope of a horizontal line? That slope is 0 because there's no rise. Okay, there's no rise to a horizontal line. So the slope of a constant, or excuse me, the derivative of a constant function is 0. While we're thinking about it, since we're talking about horizontal lines, let's talk about vertical lines for a second. Think about a vertical line. What kind of slope does a vertical line have? It has an undefined slope. So that's something to just kind of keep in the back of your mind. Okay, so here's the power rule. If n and a are rational numbers, okay, rational just meaning that it can be expressed as a fraction. So that includes whole numbers. That includes a lot of your decimals can be written as fractions. 0.5 is 1/2. 0.75 is 3/4. 2.5 is 5/2. Okay, those are rational numbers, positive and negative, and 0 is included in that. Then the function f of x is equal to a is a rational number, fraction, whole number, whatever it may be, it's a constant there, times x to the n is what we call differentiable, which is just a fancy way of saying you can find the derivative. And the derivative is n times a times x to the n minus 1. So what happens is our exponent comes down in front of our constant. We're going to multiply those two numbers, okay? And then we're going to take 1 away from the exponent. Now, for the function to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. That's a little confusing, but when we get to an example where it doesn't work, I'll point it out. Okay, so here's a function. Okay, let's look at this. F of x is equal to x cubed minus 4x squared plus 7x plus 8. Now, if I asked you to find the derivative of that using the limit definition, let's just start writing that for a second, okay, so that we can grasp how much easier it is if we don't have to do this. Look at what we would have to do. We would have to cube x plus h, then we would have to square it, multiply it by -4, add 7 times x plus h, plus 8, and then we would have to subtract f of x. I don't have room to write it, and then divide by h. That's a whole heck of a lot of work. But we know the power rule, so guess how easy this derivative is. The derivative of x cubed is 3x squared. The derivative of -4x squared. We bring, let me kind of show you how it works here. Okay, the 2 comes down, times the 4, and then we subtract 1 from the exponent. The derivative of 7x, again, let's kind of look at it in terms of the rule here. The exponent here is 1, so it's 1 times 7, x to the 1 minus 1. And we just said that the derivative of a constant is 0. So let's clean this up a little bit. 3x squared minus 8x plus 7, because x to the 0, anything to the 0 power is 1. So here's our derivative. So much easier than the limit definition, right? Okay, let's look at example B. G of x is equal to the fourth root of x minus the cube root of x plus 6. Well, you may say, well, there aren't any exponents there. Don't forget, we can rewrite radical expressions as rational exponents. Remember, power over root, so that's x to the 1/4 minus x to the 1/3 plus 6 is really what that function is. So now we can apply our rule. So we bring down the exponent, we subtract 1 from the exponent. So bring down the 1/4, keep the x, subtract 1 from 1/4, we get -3/4. Minus, we bring down the 1/3, we subtract 1 from the 1/3, the derivative of a constant, the derivative of 6 is 0. Now, since it originated in square root, or not square root, but radical form, we need to put our answer back that way. So negative exponents, a little review here, negative exponents go in the denominator. So that is going to go in the denominator with the 4. So that is 1/4 times the fourth root of x cubed. Minus 1/3 times the cube root of x squared. And then we don't need to write plus 0. Again, so much easier than the limit definition, right? And it's also easier when you're putting a string of them together. Okay, not a big deal if we just have a single term, but if we have a polynomial or something like that, it's going to take a long time to do the limit definition. But with the power rule, it's quick, clean, and easy. Okay. All right. C. The key to C is this has to be in the numerator first. Okay, this has to be in the numerator first. So we need to use negative exponents to move that x squared to the numerator. So this is really y equals x to the -2. Then we can apply the power rule, and I'm just trying to use some different notations for the derivative so we're familiar with them all. Okay, bring down the exponent, subtract 1 from the exponent. Let's put it back in its original form. Let's get rid of that negative exponent. Okay, so -2 over x cubed is dy over dx. Or we could also write y prime. Those are both acceptable notations if we start with y. D, similar, okay, similar, but we've got to be careful with this, okay? It happens every year, somebody messes this up. The x moves, okay? The 2 stays where it's at, only the x moves. Most people mess it up when the 2's in the denominator, okay? The 2 does not move. All right, only the x moves. So f prime of x is -1 times 2 times x to the -2. So when we clean that up, that's -2 over x squared is f prime of x. So pretty straightforward and easy, right? Let's do a few more examples just to make sure we've got it. Figure E, f of t. Just mixing up the variables here, okay? This tends to mess with people. -4 t squared over 5. If it really bothers you, you can rewrite it this way. -4/5 times t squared. Okay, -4/5 times t squared. That's fine. So f prime of t is equal to, bring down the 2, keep the -4/5, subtract 1 from the exponent. So if we fix this up, that's like 2 over 1, so that's -8 over 5. And you can put the t there, or you can put the t beside the fraction, whatever you want to do. Either one is acceptable. Probably you're going to see it in the numerator, just because it takes up less space in printing. Okay, f. We've got 2 times the square root of x. Again, remember, we need to rewrite that square root as the 1/2 power. So let's use y prime this time. So we've got 1/2 times 2, x to the -1/2. And that equals 1/2 times 2 is 1. So that's just 1 over the square root of x if we get rid of the negative exponent and put it back in square root form. Okay, here's an example of what I was talking about. This is the one that people always mess up. Okay, this 2 right here has got to stay in the denominator. Only the x gets to move because only the x has the exponent of the 2/3. The 2 does not have an exponent here. I mean, technically it does. It has an exponent of 1. So if you wanted to move it, you would have to move that up as 2 to the negative 1, okay? The 2 has to stay in the denominator. And I'm emphasizing that because it happens every year, over and over and over again, so I'm trying to preach it as hard as I can from the get-go. Okay, so bring down the exponent, multiply by the constant that was in front, subtract 1 from the exponent. So if we're subtracting, let me show you this one. If we're subtracting 1, we need 1 to have a denominator of 3. So we're subtracting 3 over 3. So let's simplify. These 2's in front cancel. So we've got negative 1 over 3. When we subtract those exponents, negative 2/3 minus 3/3 is negative 5/3. So let's put that in the denominator. So it's the cube root of x to the 5th. To get rid of the negative exponent, we put it in the bottom. Power of a root, it was 5 over 3. So power of 5, root of 3. Okay, so I want you to practice with this. Okay, pretty easy, but you got to make sure you got it right. So on textbook page 143, I want you to do 3 through 18. Shouldn't take too long, but make sure you've got them correct.